Welcome. I want to say a little bit more about this Morse Sard theorem, which we have looked at last time. It can be done both in graph theory or in the language of simplicity complexes or delta sets if you really want the topos to work with. And so this is framework which is very, very general. What we are looking at is level surfaces or codimension 2 surfaces. And I want again to look at codimension 2 surfaces, maybe because of a physics story. I mean, I like the Mickey Mouse story, the Mickey Mouse mathematics. Our universe for our space-time will be just a very, very small graph with 10 nodes. Or we can also take larger ones, but then we can look at the level surface of a random function or the level codimension 2 surface if you have two functions. And I like in the physics framework also to think about the two functions as a complex function. So a function from G to C produces you level surfaces. And also because we are teaching multivariable calculus, this is also a framework for Lagrange, right? You are looking at functions on a constraint. So you extremize a function on a constraint. And then it's very clear what you mean with a critical point. Critical point is just a point where in the unit sphere you don't deal with spheres. So a manifold has the property that when you look at the unit sphere, then you have a sphere. If you have a surface, you look at the unit sphere in the surface, then you have a sphere. So that characterizes manifolds, and that's how manifolds have been defined. And if it's not a manifold, if it's locally not a sphere, this is replacing linear algebra. You look at sphere geometry, it has a very natural discrete story. And I like this physics, especially because there is also quite a bit of popular mathematics associated. Hawkins at the universe as a four-dimensional sphere, right? There's no boundary condition, so you start at one side of this is maybe the Big Bang, and you go with time through, and then you have the big crunch. No boundary condition. It's very elegant. Oppenheimer is the latest example where quantum mechanics really appears, and it's nothing else than it's just a complex valued function which moves in time. I like the Wigner picture. The Wigner picture is if you look in space-time just at the eigenfunction of some Laplacian, and then you can look at specific times, you see what happens with this wave, and so you have an evolution by just going through, making cuts through the manifold space. I play with this just, this is my universe. You see the graph, right? It's a very small graph. It's the smallest four sphere. This is the smallest four-dimensional polytope in dimension 5. I'm a big fan of polytopes, and sacred geometry deals with polytopes, but you can do that in any dimension, and they exist in any dimension. And then you can of course look at more complicated spheres. You can take random functions. I took some random function here, and what I obtained is I obtained two polyhedra, two-dimensional spheres, as it should be, right? That's what Sard's theorem tells, that if you take a level surface, a codimension 2 surface in a four-dimensional manifold, you get a two-dimensional manifold, or empty. And so that's very nice, and so we can play with this. And I also like the story of Chladni, the Chladni figure. So the place where the function, where an eigenfunction is 0, this is a place which doesn't move when you apply the wave equation. Right? If you look at the wave equation, UTT minus LU, where L is the Laplacian explicit solution of the wave equation. And so the places where G is equal to 0, that's the places which do not move. That's where the sand goes if you look at the Chladni. I unfortunately don't have a Chladni kind of framework, but I have here just something which vibrates. And so what happens is, this is my plate and there's sand on it, and I'm vibrating. Of course, this is now not an eigenfunction. And what happens is, if you have the right frequency, the frequency lambda, which is an eigenfunction, which means LU is lambda U. Doesn't depend on time, and then you can write down the solution. Stationary solution gives you then an ordinary differential equation. From the PDE partial differential equation, you get an ordinary differential equation. And these nodes, these Chladni nodes, are the places where the sand goes. And you can see that on a violin. Like the red violin has a scene where they actually use some setup to find out why this red violin sounds so nice. And there's also the relation with the string theory. String theory is out of fashion because it obviously didn't work out. You know, we have mathematical theories, and most of these mathematical theories, of course, are not realized. That one knows since the 30s. There's Gödel has already shown there are several different mathematics, and so you can, in each of them, you have a framework, you have an axiom system, and then there are some which are realized in physics, a very tiny part. Not all finite groups appear in physics. Some small groups like SU2 or SU3 appear in physics, but most of the mathematical theories which you can figure out, they have nothing to do with physics. But it still exists. I mean, I'm like most mathematicians, a Platonist, so they exist. They is already kind of built there. We have just to discover it. This is not the universe. The universe has not just 10 nodes. Maybe it has 10 to the 400 nodes. Who knows? If it is a finite framework. And then what we can do is, however, we can do experiments. We can take random functions and see what happens. So in this case, I got a polyhedron, and so I can also look at larger graphs. I made experiments with holonomy sphere. Suspension of a holonomy sphere is a 4-dimensional manifold. It's not a 4-sphere, but it's also then interesting. Then you get more higher genus, more likely higher genus surfaces when you take random functions. It's very interesting also for a statistician to see what happens typically with this. What has the Euler characteristic typically for such a level surface or for a hypersurface, or if you take more functions, what happens there statistically. So it's very nice that you have also probability spaces of objects. And then I can also look at kind of the case here. That's kind of an interesting case where you have kind of some level surface, and then you take a time and you cut through the universe with different time. Then you can see these particles moving, which in this case are just strings moving around, like in this elegant universe picture, which unfortunately did not pan out for physics. The physicists, when they saw the results from the Large Hadron Collider, when the Higgs particle was found, you know, each theorist had kind of a, you know, prediction for the mass, and the supersymmetry just didn't work out. It's not a disaster for mathematics, because everything you do in mathematics is true if you prove a theorem. So this theorem is true also in 1,000 years. Also, if there is no discrete mathematics realized in physics. That's it for today.